All right, in this module, I want to talk about how we actually measure polymer crystallinity. So we're going to talk about three ways. These are not the only three ways. There are several methods and several we won't talk about, but these are the three I want to talk about. Density. So you can kind of think of Archimedes, right, and discovering kind of the differences in density. We're going to look at X-ray diffraction. We've talked about this briefly before. And thermal transitions. So detecting those thermal transitions. All right, let's start the first one because this might be the most intuitive one that you can think of. So this is density, right? So if we consider our semicrystalline polymer to be a two-phase material, then what we can think of is we can think of each phase as having a distinct density, right? So we know crystalline materials have a lower density, or sorry, a higher density than amorphous or liquids, right? So we're going to have the density of the wholly 100% crystalline phase and the density of a wholly amorphous phase. And the density of a two-phase material is going to be somewhere in the middle there. So the density of this 100% crystalline phase, as we said, this isn't very common to be able to calculate something that's 100%. So we can actually just use unit cell parameters from X-ray diffraction to be able to get this. So we kind of calculate this value. And then the amorphous density can be usually measured directly. If it can't, there's extrapolation methods where we can do so that we don't have to fully get 100%. And so we're able to basically get these values as kind of standards, and then we can calculate the percent crystallinity as somewhere in the middle between those two. And so we arrive at this equation here. And so we basically have rho as the density, and so rho C is the crystalline phase, rho S is our semicrystalline sample of interest, and then rho A, the A is for amorphous. So those are kind of how we get that. And so this is pretty straightforward. So if we want to calculate this, we would measure the density of our material and compare it to the fully crystalline and fully amorphous, which we could look up those values in the literature to determine what they are. So that's the first way. The next way is XRD. So we can use XRD as a way to quantify the polymer crystallinity because we've seen crystalline materials, we have peaks associated with certain crystallographic planes, right? That we saw that before. And so when we see those peaks, we know that we have a crystalline phase and it corresponds to one of the sets of crystallographic planes. Whereas if we have an amorphous material, we tend to get more of a broad single peak for a material, and we typically call that a halo peak. So that's kind of the blue that we see. It's not really it's really just one broad peak of everything. So that tends to correspond to an amorphous material. Whereas if you have peaks from that, it gives you crystalline. It tells you that there's crystalline phase available, and so the amounts of those peaks we can use the amounts of those peaks, the area underneath the curve, to be able to get the fraction. And so in this case, a rather simplistic way of looking at it would be to take the area underneath the crystalline but above the amorphous. Oh, sorry. So the A area, right? So that's A area, and then area C, and then area A would be the area underneath the amorphous. And so it's kind of comparing those two. So we can do quantification of this, but we can also qualitatively look at peaks, and the more and more discrete peaks that we see, the more and more crystalline it is, as opposed to just one kind of broad peak. A halo peak indicates that it's amorphous, and so we can use that in that way. All right, and the last one I want to talk about is probably the most common, and that is to look at the actual thermal transitions using a technique known as differential scanning calorimetry, or DSC. So I've got a picture of a DSC here, and basically what you see is a furnace, one kind of big furnace, and it has two chambers. You see one here and one here. So there's two chambers. One of them, for example, this one contains your polymer of interest that you want to test. And then the other is some type of reference material. So right here it doesn't have anything, but it would have a reference material that doesn't undergo any sort of melting or glass transition or anything like that. It just has kind of a uniform increase in volume and thermal properties. So how we do this, how we measure the properties, is we basically heat both chambers at the same rate. And this is an electrical furnace. So basically it's a resistive heating. So we basically have a coil that we heat up. So we apply a certain amount of current or power to the system, and that heats it up. And so if we try to heat both of them up at the same rate, there may be differences in the amount of power needed to heat the sample, right? And that's because we can have different thermal events. We could have an endothermic. So this is an event where we would need to add more power to the system to be able to heat the polymer at the same rate. Or it could be exothermic. So less power is needed because it's giving off heat. And there can also be changes in the heat capacity of the material. So all of these will affect how much power needs to go into the sample furnace in order to heat them up at the same rate. And so what we get out of that is a curve like this. So we see basically what we do is we heat them up. So here you see from 100 Celsius all the way up to 300. And you see this kind of flat line, but then you see deviations from it. So you see something here and something here. And this is heat flow. So this is that power difference in the sample. And so the first thing we see is this step change. So basically we see kind of a flat line and then it steps down and there's another flat line. So step changes like this in polymers tell us that we have a glass transition temperature because the step change corresponds to a change in the heat capacity. And that's what we expect with the TG. So anytime we see one of these step changes for a polymer, it tells us we're measuring the glass transition temperature of that material. And then afterwards, we have this positive peak. So a positive peak in the heat flow means that it's an endothermic event. So we had to add more power to the furnace in that particular chamber, which means that we have an endothermic event. So heat's added. And in this case, for this polymer, it means that we're melting the polymers. So to go from a crystalline solid to a liquid, right, we have to add extra heat. It's an endothermic event. And so that would tell us that this is the melting temperature. So any amorphous material crystallizes, we would have this kind of phenomenon. We would have the TG, and then at some point, if it can crystallize, it would, if it can melt, we would see this. So this would be for a crystalline or semi-crystalline, and then this would be for an amorphous material. But on top of this, we may also see a crystallization peak. So if it's an amorphous material that can still crystallize, you might also see a negative peak here, which would mean it's exothermic, because there's heat given off during the crystallization process. So there's actually can be a third type of peak that we see in between these two peaks. All right. And the reason we can use this to determine the amount of crystallinity is because this peak corresponds to the melting enthalpy. So the energy it takes to melt. So the area underneath this curve corresponds to the melting enthalpy. And that particular quantity can be used to determine the percent crystallinity, so XC here, because we can relate it to a 100% crystalline material. So this is another value that, again, is kind of determined based on by theory or by these highly unusual perfect crystals. So we can calculate the enthalpy for 100%, and we have that as a the ratio there tells us how crystalline it is. So that's the percent crystallinity for this material. So basically, how big this peak is relative to the 100% crystalline tells us how much material, or how much crystalline material we have. All right, so in the next module, we're going to kind of, thinking about these different methods we just talked about, work some examples of percent crystallinity from those methods.